Well, let's go ahead and start on chapter 21. And the beginning part of it is pretty much a review. So you've already learned about null hypothesis, and we have this cute cartoon. I can't believe schools are still teaching kids about the null hypothesis. I remember reading a big study that conclusively disproved it years ago. So, two parts of that joke. One is we're constantly rejecting the null hypothesis, so then why do we teach it? Or you could argue, hey, if you actually, how could you reject the null hypothesis and then, but that's part of what we teach. But anyways, moving on. So let's revisit the null hypothesis. It's always about a parameter, not your sample. It's a thing you can't prove. So usually we're moving to inductive reasoning here where we prove by counterexample rather than calculation. It's the thing you're trying to prove unlikely. We're trying to find a counterexample to disprove the null hypothesis, or at least say that it's highly unlikely. It's context dependent, so it depends on the situation. And in symbol form, it's always written as an equality. H naught equals P naught. To test it, calculate the probability that you would see that statistic, or more extreme given that the parameter is true. So what we're going to do is take our sample and say, hey, if P naught is the actual value, what's the probability I would see what I saw just from random variability? Okay. So let's go over some examples of hypotheses just one more time. A car manufacturer considers automating a production line. The proportion of defective installations for human assemblers is 0.02. So your null is always going to be just that value. H naught, you have P naught equals 0.02. In this case, you could say, well, hey, why is it less? Why are you doing less here instead of more than or not equal to? Well, if they're trying to automate a production line, odds are they're trying to minimize defects. So they're trying to make this 0.02 lower. So that's how we pick this alternative. See how it's very context dependent. People with less than 12 grams of hemoglobin per deciliter of blood are anemic. A public health official suspects that the mean for all children in Jordan is less than 12. All right. So our null hypothesis is that people are not anemic, that they do have 12 milligrams per deciliter. I'm not too worried about more than, okay? My alternative is that they are anemic, that they have less than 12 milligrams per deciliter. So this is also a one-tail, lower tail test. Here we have young women, American women aged 18 to 24 have an average height of 64.5 inches. You wonder if the height of seniors at Cedar Ridge is different than the national average. So my null is the national average, 64.5. And here I just said different. So I'm going to say my alternative is that it's just not equal to 64.5, which makes it a two-tail. All right, now let's look at alpha levels and statistical significance. We have been using an alpha level. We haven't been calling it that, and that alpha level was 0.05. And that's what we compared the p-value to. This threshold, again, is called the alpha level, the 0.05, not the p-value, but the 0.05 where we set it. Now, if our p-value is below alpha, we can say the data provides sufficient evidence to reject the null hypothesis. In other words, it's kind of unlikely to see this result given just normal variation. If our p-value is above alpha, that means our result is more likely. Then we can, just due to random variation, then we say we fail to reject the null hypothesis. The data has not provided sufficient evidence to reject the null hypothesis. Those are two ways to say that. Never say the word, we accept the null hypothesis. That's a big no-no. Occasionally, I'll accidentally say it, but we don't do that. All right. Now, how to interpret p-values. Remember that the p-value is the probability that we would have gotten what we did, or more extreme, just by a plain old random chance given that H naught or null is true. So the p-value is the probability of getting the sample result given H naught. It is not the probability that the null hypothesis is true. Okay, big deal. Always provide the p-value so the reader can also come to their own conclusions about the test. Here's an example of interpreting a p-value. Genetic inheritance predicts a 50-50 split of birth genders among embryos. A study looked at the sex of the firstborn child of a random sample of couples with 2 children. And so they found 13,000 roughly boys among 25,000 firstborns. So their p-hat was 0.5172. Well, our null is that p-naught is 0.5000. I'm just putting the same number of significant digits as my p-hat. My null is that it's actually, my alternative is that it's more than that, okay? So you can actually go ahead and calculate a z-value. And when I find it's 5.49, that's a really high z-value. The probability of getting that far away from the mean is 0.0005 or 0.05%. Not 5%, 0.05%, less than 1%. So based on such a low p-value, I don't even have to argue about alpha because this p-value is pretty convincing. The probability of observing a proportion of 0.5172 boys or more among firstborn children due to natural variability is 0.0005. It's less than that. All right, given the null hypothesis that 50% of the firstborn children are male. So we're going to reject the null in this case. All right, more about tests. So talking about type 1 error and type 2 error, and I found this cute cartoon. Type 1 error. So we assume the person is not pregnant, and we do a false positive, and he tells them he's pregnant. Obviously, not true in this case. And then the type 2 error, so the null hypothesis for both of these is not pregnant, that you're just walking around like normal. The alternative is pregnant, all right? Type 1 error only occurs if the null is true and we reject it. So not pregnant, and we reject it and say, yep, you're pregnant. Type 2 error occurs when we reject, when the null is false, so actually you are pregnant, all right, but you say the opposite, which is not pregnant, okay? By the way, these two errors cannot occur at the same time. You're either pregnant or you're not. So type 1 error, our defendant is innocent and we find him guilty. So what that means is we mistakenly reject the null hypothesis. So this is type 1 error right here. If we gave this verdict, if he was innocent, we said not guilty, we never say innocent, then we're okay. But if he is not guilty and we find him guilty, that's a type 1 error, okay? The probability of doing this is whatever alpha is, unless you use 100% confidence interval, which means alpha is actually 0. Not very useful, all right? Now, the type 2 error is when the truth is that they are guilty, all right? So we mistakenly fail to reject. If he is guilty and we say he's guilty, we didn't make an error. But if he is guilty and we say he's not guilty, that's where the error happens, all right? Don't worry, you generally don't have to calculate this probability. One thing you do need to know is that, remember, you're either on the left or you're on the right. So if this is alpha, the probability of this is 1 minus alpha. If this is, and you're going to find the probability of this is beta, then the probability of this is 1 minus beta. And that you should be able to do. If I give you one of the probabilities, you should be able to find the other. All right, which type of error is worse? Well, it depends. In the jury trials, we try to minimize convicting innocent people. So we would say that in the U.S. Criminal court system, type 1 errors are considered the worst error. That is convicting someone who's innocent of a crime they didn't commit. But let's say we're doing a medical test and we're trying to diagnose for cancer. In that case, the worst error, so the type 1 error would be, that we reject the null and say they have cancer. So the null is that they're healthy, and then we say they have cancer. That's type 1. Type 2 is they actually have cancer, but we say they're healthy. So type 2, we would argue in this case, would be the worst result because you want to catch the cancer and treat it. Whereas here, if they're healthy and we tell them they have cancer, once we start to do something, we'll probably discover they really don't have cancer.